Hello everyone. In this session, we are going to discuss about the gradient descent concept, which is the continuation to the previous topic, uh, like the fast food problem. In the last session, in the fast food problem, we discussed about the regression-based problem, and also we discussed about the loss function, meaning that the error term, how to calculate the error term. So in this session, by using that error, how can we update the weights as we discussed in the previous sessions? The main concept of the deep learning is the updation of the weights. So how can we update the weights by using that error term that we will discuss in this session? So in this, we are going to discuss about gradient descent and then delta rule and also learning rates, and then we can discuss about the gradient descent for the sigmoid neurons. So the gradient descent, if you visualize in the different angle, meaning that if you want to visualize the graph, we can take that the W1, W2. Actually, our basic equation is y equal to W1 x1 plus W2 x2 plus W3 x3 plus and so on Wn xn. That is the basic equation for the linear model, right? For that, I am taking only two parameters, just two parameters, x1 and x2. For those, we have the two weights, that is W1 and W2. These are the two weights. According to these two weights, we cannot modify the x values, x1, x2. We can modify the values of W1, W2. We will initialize the W1, W2 as the random values, and then we can go for the updation of the weights, W1, W2, according to the loss, based on the loss calculated, loss or error calculated. Based on that, we have to modify these two. So if you continue this process and if you maintain a graph, we will understand that at some point the error may be very less or zero error also. Our main aim is to make the zero error. So of course it is not possible for all the situations in the data science or in the machine learning or deep learning algorithms. We have to minimize the error. So how can we do that? If you observe in this unit, in this diagram, see here, this is the W1. Yeah, yeah. This is the W1, W2, W1 and W2, and this is the error. This is the error. So we can take some point in the combination of W1, W2 because we will initialize something. So if you take the W1, W2 at this place, the error may be here. This may be the error. After applying these weights in the equation, we may get some value. For that, if we calculate the error may be here. And if you take this point, this may be the having this error, and if you are able to fix at this position, then the error will be zero, meaning that we have to find this, what is this point. This point is important, meaning that we have to find the proper W1 value and proper W2 value. If you are able to find this, then our problem is solved. So how can we do that? For that, there are several techniques available, statistical methods are available, and also by using the variance concept, covariance of x comma y by variance of x, like that we have different methods, statistical methods to estimate these weights. And also we have the another concept that is called the gradient descent. In the gradient descent concept, actually we have to take, our main aim is to minimize the error. For that, we will take the random values of W1 and W2, as we have seen that in the example. We are taking only two variables. For those two variables, two weights are there, W1, W2. For that, we will take the random values, and then we are representing that in the 2-dimension and 3-dimension graph. Third dimension is the error. So we are plotting already. We have seen that. Now our point, our main aim is we have to make the zero error, so that to make the zero error, how can we modify the W1, W2? Meaning that with respect to E, we have to modify the values of W1 and W2. Please remember this point. And now, if you want to modify this, we have to move the values of W1, W2 in some direction. Whether you want to take in this direction, this direction, this direction, which direction you want to change, that is called the gradient. Meaning that what is the direction you have to modify the W1 or W2? That direction is the gradient. Let us say, for example, W1 is there. W1 is here. We have taken W1 is here. Okay, meaning that we will take this point. From this point, where we have to move, whether you want to go in this direction, in this direction, in this direction, which direction you have to move, that will be decided by this gradient. And W2 is also here, so where we have to move the W2 point, whether we have to move this side or that side, meaning that whether you want to, the W1 can be moved in this side or this side, where you have to move, what is the direction you want to move, this side or this side. The direction will be decided by this gradient. W2 also, whether you want to move this or this, that will be decided by the gradient. So if you calculate the gradient, meaning that derivative of error with respect to W2, you will get the gradient for W2. If you calculate the derivative for error with respect to W1, then you will get the gradient for W1. How much? Meaning that in which direction you have to move, right? So the direction to move the W1, W2, that will be represented by the gradient. And now the gradient descent algorithm, what are the steps? Initially, we will take the random weights, random values in the weights W1, W2, and then we will go with the plotting of the graph. In the plotting of the graph, actually we are plotting only for W1, W2, so that we are getting these circles. So here our main aim is to reduce the error. The reduce the error means it will be here only. This is the less error. All these are the various having various errors. So we have to move close to the less error. That is our main aim. So for that, what we will do is evaluate the gradient at the current position. We will take at this point, we have to evaluate the gradient at the current position, what we have to modify, in which direction we should go. That will be decided at this current position, and according to that we have to take the steepest descent, meaning that we have to find the direction of the steepest descent, and we have to take that step into that direction, and then again we have to calculate the gradient for the new point. From the new point, what is the gradient we have to calculate, and repeat this step until you get the very less error. Sometimes you may cross that, and you may get the increasing of the error, so that we can stop at that moment where we are getting the minimum error. There we have to stop, right? And it tackles the problem of the training individual neurons. For every neuron, this is the concept for every neuron. Okay. Now let us go with the learning rate. Another point is here, we have decided by using the gradient descent, we have decided in which direction it has to move, but how far it has to travel, how far it has to modify. The direction is fixed, but how much you have to travel in the W1, in the W2, how much you have to, that will be decided by the additional parameter, that is called the hyperparameter. The hyperparameter is the additional parameter which supports the training. So this learning rate is also the hyperparameter. In the second unit also we discussed about some parameters, hyperparameters, epochs and loss functions. All these are the additional parameters, hyperparameters. So learning rate is also another hyperparameter that specifies how far the parameters have to move in the specified new direction, right? That will be decided by the learning rate. Now this distance, it needs to depend on the steepness of the surface. On the surface, how steep it has to move and how far it has to move, that will be decided. But it is also very difficult task. That actually that factor is represented with the epsilon, in that we can specify that, of course, in different analogies and different techniques in the different textbooks, they have mentioned with the different things, that we can say that alpha, sometimes it may be referred with alpha. Here in your textbook it was specified with the epsilon, and in that picking that what is the learning rate, that is also very important, crucial role, it is playing the crucial role. And if the learning rate is too small, then it will take a long time to reach the minimum error. If you have taken the large data set, meaning that the large step, then you may cross the minimum. You may cross the minimum, the W1 weight, you may cross the minimum, so that it will miss the minimum. So these are the two problems. So because of that reason, we have to take the optimum value for the learning rate. Of course, there is no thumb rule for taking the learning rate, how much you have to take, that we don't know. Depending upon the data set, on the spot we have to take the decision, that's it. Okay, there is no standard rule how much you have to take at this moment. Now we have to go with the delta rule. This is also another important point to be considered before going into the gradient descent algorithm. Now delta rule means, see, we can see that here to calculate the each and every way, we have to evaluate the gradient, right? For the gradient, the partial derivatives, we have to find the partial derivatives of the weight, each and every weight with respective, we have to find the partial derivative of the error with respective to each and every weight, and then based on that you have to modify the weights as we discussed. So see here, so delta WK, meaning that the K weight, I want to modify this, I want to calculate the gradient for WK. For that, what we can do is, we have to calculate the derivative of the the gradient for dou E by dou WK. It represents the derivative of E, that is the error with respect to weight WK, and we have to multiply that with the epsilon, that is the learning rate. We have to multiply the calculated gradient with epsilon. So this is the weight we have to calculate. For this, how can we calculate? Actually E, already we have the value E, meaning that what is the value of E? We have the equation for E. Already we have taken that mean squared error. The mean squared error is this one. This is the mean squared error. In the place of E, I am writing this. So here dou by dou WK of 1 by 2 into sigma Ti minus Yi square. See here, here we have to calculate the error for mean squared error for the instances. We have to calculate this, and then for the number of instances, how many instances are there, for those instances we have to calculate this. This I represents, on the top it will represent the layer as we discussed in the previous sessions. Now see here 1 by 2. Why we are taking 1 by 2 here is, generally 1 by m or n we will take, but here we are taking the 1 by 2. Why we are taking 1 by 2 is, this is because the derivative will give you the 2 here. So to cancel those 2, we are taking the 1 by 2, that we will do it. See here, and that will be given like this. See here, in this there is the square. dou by dou wk, that is here with respective to w, the w is involved in the y term, right? So in this, to calculate the y, we have the w term, and for this anyway we have the base here, that exponential here, that will come forward, so that the 2 will come here, so that these 2 will be cancelled, and we will get only the sigma t minus y. Epsilon is also there, epsilon is also there, epsilon and ti minus ty, and the w term is involved in this. Because of that reason, we have to give the dou yi by dou wk, since it is involved, and everything will be come out from the derivative, so that here y dou yi by dou wk, and for that see here we are taking this do this yi means, the y means, this is the formula for y, w1 w1x1 plus w2x2 plus w3x3, like this. So in our example, if we have only two w1 w2, then we have to take up to w1 w2 only. Now if you apply that, then for which you are applying the wk you are applying. So w1 w2 w3, all these will be cancelled. What is the k? Only that term will be remaining. Let us say for example k equal to 2, in this situation this term will remain, and remaining will become as the zeros, so that we will get this. For this, the derivative is whatever you have with the derivative formula. We are getting that this w2 will be eliminated and x2 will be given. So this one will be here. So that whatever k is there, that k will remain in the equation. So sigma epsilon xk into pi minus yi. So this is what we have already calculated. So this is the delta rule concept.